So now in the future, I think this is already happening. I think the development is to say we are not just interested in establishing which proteins are in what sample, but that we can measure large series of samples, let's say clinical cohorts or time series, or follow the consequence of a knockout in cells. Basically have large cohorts of hundreds, potentially thousands of samples. And we would then measure protein patterns that reflect the response of the cell or the tissue or the human to a particular insult, for instance, a disease or a genomic variant. And that now these data can be then matched with the fantastic capabilities of high-end computing, machine learning and so on, to learn basically a data-driven make new biological findings. This is already happening. It will happen a lot more in the future, and so I think the development has been to make basically the proteome measurable and as an entity, and now to apply this to large numbers of samples in suitably constructed sample sets.
Spectrometry is actually a relatively young science, and mass spectrometry applied to analyze proteins in clinical samples is even a younger part of that young family. There are growing pains, and 20 years ago, when we first started applying mass spectrometry to analysis of proteins, we tripped and stumbled quite a bit, like a toddler learning to walk. And some of the community hasn't realized how far we've gone and how far advanced we are and how mature the science is and how much better we are at reproducibility and robustness. The answer to my earlier question about what's the biggest advance in proteomics, and that is the reliability, the reproducibility of the quantification. That's really more important than sensitivity. People have to have confidence in our measurements, and people are just more familiar with antibody-based, and it's easier to implement. Mass spectrometry can be scary. Which button do I push? How do I inject? What parameters do I need to set? So I think it's still just a matter of evolution. I think technically we're still handicapped by slow throughput and by the expense and complexity of our instrument. But if we were to focus on targeted mass spec assays that addressed a very defined question, I have every confidence in the ability of engineers to build a black box mass spectrometer that could be as easy to utilize as an ELISA assay. But we need to know what assay we're trying to build.
It's absolutely essential. We can't sit in a silo and only look at one omics. We have to relate the glycomics or glycoproteomics to the proteomics, to the genomics, to the metabolomics, because these are real cells. They're not just molecules floating around. With the glycoproteomics, we need to look at the genomics of the enzymes which synthesize these glycoproteins, the pathways that are involved, the cellular bodies that are involved, and the metabolic outcomes of them. So none of the omics can live in isolation.
Few words I will speak about the ECR of UPO. It's an early career research initiative initiated by UPO within UPO and with the support and the mentoring of the HPP. The goal of ECR or how this was born is in the fact that the new generation of scientists in proteomics were interested to know what was also happening in the past, so on what we are building our current activity in the future. So we wanted to get in touch with the generation before us, which put in place all the things which we are using now. And so we had the chance to interact with them, and we slowly become a platform where we're trying to put together the scientists in proteomics, the young scientists, and connect them with what is going on within this time, but also with the past, and with what will be in the future, we hope. And this is really the scope of our initiative, to connect generation and connect people of the early career stage in their career, obviously.